Had to get the microphone working. Sometimes it's good just to unplug it, plug it back in. Sometimes things work. All right. All right. Guess we're good. So, had the exam on Friday. Sent out an announcement. So while you were taking the exam, if you happen to have encountered an issue where the figure didn't show or it didn't load, please email me. Tell me what browser you were using. And I will be emailing our instructional technology people. As far as I'm concerned, it's inappropriate. And I know when I've had some issues, I've contacted them and they've told me, oh, well, you should use Firefox instead. And it's like, it shouldn't matter. You know, say it's 2020, it shouldn't matter, but sometimes it does. So a couple of you have already emailed me. Thanks. But if you did have some issues, please email me. And then we'll go from there. All right, so this is where we left off. Spatial dispersion. All right, so 3 fundamental characters of populations. We have, population size or density. We have our spatial distribution across the landscape, which is dispersion. All right, and then we have demographic characteristics. So we're on number 2 right now, dispersion, and this is going to be the focus of this week's lab. So bring your calculators to lab. We have computers there. You can do some calculations. You'll learn how to, we'll check our ragweed, see what pattern ragweed has. All right, but what patterns are there? There's basically 3 patterns. Random distribution. All right, that's going to be our baseline. All right, and then you have a uniform regular distribution or a clumped or aggregated distribution. We detect these based on something called the coefficient of dispersion, which is basically just a variance to mean ratio. It looks at the variation in our numbers and our data and compares it to the average. Because when we deal with spatial patterns, if it's random, the variance and the mean are going to be equal. So if our variance and mean is equal, then that suggests we have a random pattern. If our variance is less than our mean, it suggests we have a uniform or regular pattern. If our variance is more than our mean, then we have a clumped or aggregated pattern. So let's talk about each of these in a little bit more detail. So clumped or aggregated is a case where our coefficient of dispersion exceeds 1. Our variance is more than our mean. And as you'll see in the lab, it's not going to be, we have some variation. If we repeated it over and over again, we could get a value of, let's say, 0.99, could get a value of 1.01. Those are random. All right, we're talking about the pattern of, let's say, 1.2, 1.3, something that's unlikely. It's a value we would unlikely to get just through random chance. All right, so our variance to mean is greater than 1, our coefficient of dispersion is greater than 1, and we have this clumped pattern. What that basically means is that the presence of one individual makes it more likely that we find another, because our individuals are occurring in groups. They're clumped together. All right? This is probably the most common dispersion pattern that's out there. All right? And the question is, why? Why would it be? Well, there are several factors that favor this type of pattern. All right? Number one is related to transmission of our pathogens, so transmission of bacteria and viruses and so forth. And we actually see it here. See what's happening this year with COVID-19. All right? The infections exhibit a clumped or dispersion pattern. Why is that? It's because the transmission of the virus needs close contact. So in areas where we have high population densities, you have these outbreaks. If you go out to one of these small towns where there's only 200-300 individuals, it's unlikely that you would get it out there. And even if you do, it's not going to spread throughout the town like it did in, let's say, New York or Chicago or Philadelphia and so forth. Dispersal stages is another aspect. So the dispersal stages that we can talk about are, let's say, seeds. All right, plants can't have, their seeds don't get up and fly away. They don't, have wings at the sprout and then carry them out to different places. A lot of times their seed dispersal depends on whatever mechanism they utilize. So acorns, they fall, hit the ground, and they're going to stay there unless something picks them up and moves them. Ragweed, mosquito flying around here. Ragweed seeds disperse out, let's see here, ragweed. Ragweeds are not wind-derived, I don't think, but dandelions are. Dandelions get those puffy white seeds. That's carried by wind. So if you think about it, if you have one individual produce the seeds, all of those seeds are likely going to land within a set range of the parent. And thus, over time, you'd get patterns like this. Habitat heterogeneity is another factor. So what does that mean? Well, it means that our landscape isn't uniform, that we're going to have patches of good habitat, patches of not so good habitat, and our individuals are going to try to flock or cluster around or in areas of good habitat. Social patterns can produce this. And with social patterns, I said gregariousness. So gregarious natures is more of a social type of behavior. By default, humans tend to be social in nature. We tend to be gregarious, and that's different than an organism that's not gregarious, meaning they tend to live in isolation. They tend to be alone throughout their life. So if you're dealing with a species, especially an animal that is very social, then they're likely going to live in groups. They're likely going to exhibit this pattern. Reproductive behaviors can also produce this. Now, it might not be year-round. It could occur only during, let's say, the mating season, but it's the same type of idea. Our individuals have to come together. They have to go through mating rituals, mating procedures, and during that time, if we sample and survey our populations, we can get this aggregated distribution pattern. Lastly, weather and environmental conditions can produce this clumping. I think the best example is, let's say, extreme cold that happens. Cold spell, oftentimes you can have organisms that kind of clump together, huddle together to try to keep warm. That produces our clustering. Perhaps weather changes and it sets up the habitat heterogeneity, so some areas are better to weather the storm, you can say, and that leads to this clustering. All right, so all these factors, they contribute to this pattern, and that tends to be the reason why this is the most common dispersion pattern. Second one that we'll talk about is random distribution. So this is a case where we need our variance to mean ratio to be equal to 1, so our coefficient of dispersion is equal to 1. And the presence of one individual in this case doesn't affect the probability of finding another. It's just completely random. So if we go out and drop our grid, we have maybe a baseline probability, 10 or 20%. Let's say 20%. We drop our grid out there for ragweed, we have a 20% chance that we'll have a ragweed in there. All right? Just because we found one ragweed in that grid doesn't mean that it's now more likely that we find another ragweed plant in that grid. It still stays at that base 20%. Now, in this one, we don't necessarily have factors that favor the pattern. We actually have some requirements. All right? So in order to have a random pattern, we can't have any sort of habitat heterogeneity. We need a uniform environment across the landscape so that our individuals or organisms are not going to favor certain locations. We need a uniform environment, and this applies both spatially and temporally. So we can't have situations where environment changes tomorrow, making certain areas of our habitat more favorable. We can't have that. We need a uniform environment so that our individuals can live everywhere in our landscape. And the second requirement for this pattern is a neutral intraspecific interactions. So our intraspecific interaction is the between species interactions. Right? Individuals of the same species are going to interact with each other. We need neutral patterns. We can't have positive interactions. We can't have negative interactions. All right? Going back to this clumped or aggregated pattern, you could say this is kind of positive interactions, especially if we're dealing with social behaviors, with gregariousness. All right? Having one around is positive. It's going to influence that other individual to try to stay around. For random patterns, we can't have that. We can't have that positive nature. We also can't have the negative nature. We can't have this extreme competition preventing others from getting close to us. All right? So random pattern, it's got to be uniform, and we have to have this neutral intraspecific interactions. And our last pattern is this uniform or regular pattern. So I'd say this is kind of like a Christmas tree farm or orchard where all of our plants are equally spaced. All right, all of them are equally spaced. And because they're equally spaced, we have very little variation in our distances. Very little variation in what we see in our grids. So our variance to mean ratio, our coefficient of dispersion, is going to be less than 1. There are some factors that favor this. All right. The first factor, probably the most common, is a very strong intraspecific interaction. And the intraspecific interaction that we need is repulsion. We have to have our individual that is going to actively repulse other individuals from getting close to them. All right. Creosote bushes. Acecrete compounds from their roots prevents other plants from getting close to them. And thus, if you go out and look at the creosote bushes, they tend to exhibit more of a uniform or regular pattern across the landscape. You know, you've seen king penguins. I'm sure you've seen that, where they are all standing on the ice, you know, basically wings length away of each other. That's a uniform pattern. It's because of this repulsion. Very territorial. Individual gets close to their space, they are very aggressive. All right. Second factor is dispersal stages of some of our plants. All right. Not all of them, but some plants have dispersal stages that favor this type of uniform or regular pattern. Any questions? So this dispersal stages of plants. This forms the basis of the Jansen-Connell hypothesis that leads to this idea that seed predators and herbivores together are responsible in producing our uniform distribution pattern of plants or the random distribution pattern of plants. All right, so it's the seeds that then attract our seed predators and herbivores. And then those types of interactions, those interspecific interactions, is what generates this observed dispersion pattern, uniform or a random pattern. So how does this work? How does this work? So what you recognize is that we have a tree. that produces a lot of seeds. Diagram this. So we have a tree that produces a lot of seeds. So these are all the seeds on the ground. This represents a pretty large food supply. They're all clumped. The seeds themselves are clumped. If you think about it, if we're actually germinating, it would produce a clumped or aggregated distribution pattern. But then you have some seeds that can fall far away from the plant. Maybe an animal picked them up, started carrying it away, and then got scared and dropped it. Sometimes maybe it just hit a rock and it bounced. Who knows? All right? What has happened is that this adult tree produced so many seeds underneath it that started attracting our seed predators and our herbivores. So our predators then came around and started feeding on all of these seeds. And you have intense predation. Eating up all of these seeds. They get there, they know they're there, they spend a lot of time searching, they out there and take every single seed that's there. Are there any seeds that germinate? Yeah, some of them will. They did it again. It's right there. Lights go out. Some of them do germinate, but again, that opens up the herbivores. But what ends up happening is that these seeds farther away, they're not in this group. So our seed predators came around, they spent a lot of time finding here, and there's some trigger where our predator comes around, starts looking. Maybe if they don't find a seed within a certain set amount of time, they move on. All right? But once they find a seed, they stay looking. And when they move on, they're just not moving on like another foot and looking around. No, they are actually moving around. So they come in, they feed, they can't find a seed, they move on, and they bypass all of these guys. All right? So most of our seeds around the tree are consumed, but it's these more distant seeds that have started to avoid our seed predation. And it's going to be these seeds that can germinate and grow up to other trees. So instead of having this clumping aggregated pattern around our adult, like we often see with our weeds, right, what we end up getting is you get an adult tree here, and then you get an adult tree out here, all because these more distant seeds evaded the seed predation. That's what these graphs are showing. All right, so if we look at the number of individuals as a function of our distance from the parent tree, yeah, we have a lot of individuals. That's because of our seedlings that developed. All right? It's because of the seedlings that some of the seeds are going to germinate. As we get farther and farther away, it becomes less and less likely that we'll have individuals. However, when we actually look at survival and factor into seed predation and herbivory, we get a pattern more like this. So when we're real close to the tree, we don't see any new individuals, any new adults that can come in and take that spot. All the seeds have been preyed upon. All of the seedlings have been eaten. It's only when we get farther away from the tree where we escape the predation, and now we can start getting more adult trees developing. This leads to that uniform pattern. This leads to a random pattern, oftentimes out in a forest. This is the Jansen-Connell hypothesis. You had to have a way to kind of explain how we get these patterns, and I think the seed predation and herbivory is a pretty good idea as to how that could actually work. Questions? Any questions? All right. If we have no questions, we will move on. All right, so this kind of represents a summary of this presentation. Populations, right? It's a group of conspecifics in a particular area. All right? That particular area needs to be defined. All right? And a lot of times that area gets defined by us, but if we're going to be real technical, then it's going to be defined based on demographic discontinuities. So changes in our populations, changes in maybe a birth rate or a growth rate or mortality rates, all of those things. The key for us is to make sure we have an area defined where all of our individuals can interact. They don't have to randomly mate with each other, they just have to be able to interact. All right? That forms the basis of our ecological populations. If we're interested in evolution, then what we do is pick our area so that all of our individuals not only can interact, but they also take part in random mating. So that's the basis of our deme. So our deme was a group of individuals taking part in random mating. That's our evolutionary population. So once we've defined our population and kind of described what we're talking about, then we moved on to the descriptors of our population. We started with population size and density. All right, that's fundamental descriptor number one. And with that, we talked about overall population size, which can be interesting, but usually we have to know the total area, so we're normally talking about densities at that point. It's really the density that matters, because density is what drives some of these density-dependent mechanisms, regulatory mechanisms. Now, with the density, we could talk about crude density, which is just our number of individuals per unit area, or we can do ecological density, which now accounts for the appropriate versus unappropriate habitat. And then we talked about dispersion, so we just finished this up today. The three patterns are the uniform regular, the random, or the clumped or aggregated patterns. Make sure you know the coefficient of dispersions, all right, what those values will mean. If we say, here's the coefficient of dispersion, what's the pattern, all right? And we'll actually learn a bit more in lab. We'll talk about actually testing for significance. Is that coefficient of dispersion actually equal to 1, or is it different? So if it's different from 1, then yeah, we can say it's not random. But if it's not different from 1, then even though our value might be, let's say, 1.05 or maybe even 1.1, all right, we still conclude that it's random. Now, with this dispersion patterns, the Jansen-Connell hypothesis is kind of interesting, kind of unique to plants, because now it lays out the possibility that other species could be responsible for generating this pattern. All right? And for the Jansen-Connell hypothesis, our other species ends up being the seed predators and herbivores and so forth. All right? And our last descriptor is demographic characteristics. That is going to be the focus of our next presentation. Any questions? Give you time to write them. Hopefully self-explanatory. Whoa. Yep. Okay. So we are going to move on and introduce our demographic characteristics. Let's check to make sure we don't have any questions. Nope. All right. So, demographic characteristics. There's just a quick review of our three fundamental descriptors. We just kind of wrapped them up. All right. And this presentation is all on demographic characteristics. And the characteristics that we're going to talk about are age structures, sex ratios, and birth rates. All right, because these three things tell us a lot of information about population growth. And that's kind of where we're going. All right, so demographic characteristics. These characteristics are going to allow us to predict population growth and decline. All right? And these include the age structure, which is basically the number of individuals in each of our age categories. Now, how does this tell us about population growth and decline? Well, you can think about it as in terms of how many individuals are before reproductive age and how many individuals are past reproductive age. So if our population is composed of a lot of individuals that are going to be reaching reproductive maturity, that suggests we're probably going to see some population growth. But if the majority of our individuals are at the reproductive age or beyond that, beyond when they would actually reproduce, that's going to suggest that we're going to see population decline. Basically, those individuals, as they age, they move out of reproductive ages, but they don't have replacements. You're not being replaced in that category. All right? So looking at age structures are going to be important. Sex ratios also important in predicting population growth and decline. Now, it's probably going to be more useful in certain organisms than others, but typically when we deal with these demographic characteristics, we're talking about dioecious organisms, so organisms with male and females, individuals in our populations. And we're oftentimes talking about individuals that are probably what would be termed polygynous, right, where one male can mate with more than one female. All right? So in those cases then, the more females we have in our population relative to males, the faster our population should grow. Because again, each male can mate with more than one female. It's a little bit different if we change our social structure and we say, let's say, mating for life. Now, it's less about that sex ratios because if there's more females than males, those females just won't reproduce. They can't find a mate. So no sex ratios. There are some restrictions on making this prediction that more females compared to males means population growth. And lastly, birth rates. So with birth rates, we're talking about how many offspring are born during a reproductive event. So do we have 20 offspring every time we reproduce? Do we have 100? Do we only have 1? All right? But that's only part of the story because we also have to consider the age of our mother. So are we seeing most of the reproductive output when they first become reproductively mature and then output drops off, or is it maybe a buildup, reproductive output and then a taper? Who knows? Who knows? But we'll talk about birth rates and how they go hand in hand with age structures. All right? So we're going to start with age structure. Now, age structure is the distribution of individuals according to their ages. So how many individuals are 10 years and younger? How many individuals are 11 to 20? How many are 21 to 30 and so forth? We can do this for the human population. We actually will do this for the human population. I believe it's next week's lab is when we do these life tables. All right? So our age structure is typically presented as a life table, which is just a table that shows our age, or the number of individuals for each age. Now, how we create those tables just kind of depends on the organism and somewhat of our interest. So we can make a cohort life table or a static life table. A cohort life table is going to be much easier to produce for individuals with very short lifespans. Why is that? Because with a cohort life table, we go and follow all of the individuals that are all born at one time, and we follow every last one of them until they die. All right? So if we were going to do it for humans here, what we would do is go down to, let's say, Shannon and Community Hospital, and we could say, okay, we're going to pick out all the individuals that were born this year in 2020. All right? We're going to record all of the individuals, and we're going to follow all of those individuals until the last one of them dies. Now you can see how long is it going to take us. Is there a chance that we can actually outlive that last one? Probably not for humans. But if we were doing something with, let's say, only has a 1 or 2 year lifespan, we could do it. Because we know that once we follow them when they're born, the last one will likely die in a few years. Now, the benefit of this cohort life table is that we can calculate the age-specific mortality rate, and this rate is the actual rate. Since we followed every single individual, we know exactly when they died. And that gives us an age-specific mortality rate, a chance of dying at each age. That doesn't mean we can't get age-specific mortality rates from the second type, the static life table, but rather our age-specific mortality rate is the actual rate because we've actually measured it. We've actually observed it. So the second type of table is a static life table. This will be used more for longer-lived organisms when we don't have time and resources or even the lifespan to record them. So with the static life table, what we do is we go out and we basically sample a population at a specific time period. And then we make our table based on the distribution of individuals of our various ages. All right, so what you'll see is that you probably have a large number of individuals early in age, and then as our age categories increase, we're getting fewer and fewer individuals. From that information, we can then infer an age-specific mortality rate because of the drop in our population sizes with each age. It's not actual, it's just hypothetical, it's inferred. And why would it be inferred? It's because we don't know exactly what caused the deaths. It could be, it might be possible that we see a large decrease from 30 years old to 40 years old. Maybe that came about because some event happened in that 1 year, and those individuals were more likely to die. Yeah, war has done that. World War I, World War II, Vietnam War. That has caused some of these increases in mortality rate. Are they age specific? No, it was inferred, but the reason why you had those heightened increases was due to the years that were out there. So static life tables gives us predicted age-specific mortality rates, whereas the cohort life tables gives us more of an actual type of mortality rate. How do we do these calculations? We're not going to go over them here in lecture. That's our lab. So what we'll learn how to do is make a life table in lab. We're going to do it in lab. We're going to learn how to calculate survivorship, makes these curves, and all this other stuff, estimate population growth rates, and then there's some homework that allows you to do it again on your own. What I do want you to know is know the variable names and the definitions. So there's going to be a lot of terms in that lab, or a lot of variables that we'll calculate. You need to know what those correspond to. And I believe I do have like a cheat sheet posted on the handout section that basically says, here's the terms of our life table, here's some definitions. So feel free to use those. All right, so why do we use the life tables? Number one is age-specific mortality rates. It's a big one. All right, this is probably one of the reasons why we do life tables to begin with. So this is just one example life table. Came from the book. So this shows you the number of individuals in each of our ages. And you can see how it drops off. Well, it drops off because individuals have died. And that age-specific mortality rate tells us, basically, the chance of surviving from one age category to the next. All right? And this is the basis. This age-specific mortality rates is the basis of this column, this L sub x column, which is called survivorship. Second utility of the life tables is to calculate a life expectancy. So oftentimes we're interested in populations. An individual that's born today will have a life expectancy of X number of years. That's interesting to know, because if the life expectancy increases, then it suggests something's happening. Maybe for us, probably medical advances. If our life expectancy decreases, that's also interesting. We have to ask, why is it decreasing? What's going on? And then our last reason for doing these life tables is population growth rates. Estimating population growth rates. And we'll do all three of these things in lab. What we're going to start first is with these survivorship curves. So a survivorship curve is a graphical representation of our age-specific survival. These curves plot the log of our survivorship, the log of Lx, as a function of age. All right, so that's very important to know, that this axis is actually on the log scale. Because if we didn't do it, all of our curves would basically look the same. So once we plot it on the log scale, then what we'll get is one of three patterns. They're pretty close to one of these three patterns. We have a type 1 survivorship curve up here. We have a type 2 survivorship curve, which is basically a straight line. And then we have a type 3 survivorship curve that is like this. All right, these are three broad patterns. So let's talk about these patterns. So type 1 survivorship curve is typical of longer-lived organisms, humans, elephants. All right? These are organisms that take care of their young. They invest a lot in their offspring. And because they're investing a lot, they tend not to have a lot of offspring, especially at each reproductive event, probably only having one or two or a few. That is absolutely ridiculous. We should set a timer and every 5 minutes get up and walk around the room. Anyways, it's typical of these organisms that invest a lot in their offspring. All right? And by investing a lot in the offspring, we actually have pretty high survivorship, high survival earlier in life, all the way up until they reach old age. And then once they hit old age, that's when it drops off. And it's not really dropping off because they're being preyed upon, per se, but they're reaching the end of our lifespan. We're reaching the end of our life. Now, if you can make it out, we do have a slight dip in the very young, right here. The slope is a little bit steeper, all right? And that is real. So we do have lower survival in the very young. Childbirth is pretty dangerous. All right? The child might not survive. That first year of life, they're going to be susceptible to a lot of things, new diseases, new pathogens, predation. All right? Predation for a lot of these guys. So you see lower survivorship in the very young, but that as soon as they get past that early susceptible stage, then we have high survival, indicated by more of a flat line. And we have high survival all the way up our teenage years, the 20s and 30s, our main reproductive years, all right? Middle age, still rather high. And then once we get up to 50s, 60s, 70s, now it's going to start dropping off because we're reaching the end of our lifespan. And we'll talk about some of these characteristics, organisms, because that's related to our life histories, life history patterns. Type 2 survivorship curves are these. It's where our survivorship is basically a straight line and it's a steady decrease. Birds are a great example of these. All right? What this means is that what this suggests is that these individuals have a constant mortality rate across all of their ages. So the chance of dying this year is going to be the same as the chance of dying next year. And then cumulatively, when you factor in all of those chances of dying every year, you end up reaching basically a lifespan. And it produces this straight line survivorship curve. Now with birds, we often do see more of a segmented type of pattern. So the birds before they fledge, so the bird as they're in their nest, might have one type of survivorship curve. So might have, could have a different slope than post-fledging birds. All right? Type 3 survivorship curves are things that are going to produce a whole lot of offspring all at once. And a big reason why they do that is because the chance that one of them survives is actually pretty low. Right? Okay? So you see a lot of death in the young. A lot of them are going to die. But you don't have to have hundreds surviving. You only need a couple that survive to ensure that the population is going to be stable. So things like trees exhibit a type 3 survivorship curve. Invertebrates, many invertebrates, barnacles here in this case, exhibit type 3 survivorship curves. So we have very low survivorship curves early in life, but then as soon as we reach adulthood, we have high survivorship. So the period, the highest risk of death happens in the young for these individuals. And you could say, well, hold on, well, what about trees? Jansen-Connell hypothesis. Seed predators take out a lot of individuals. When the seedlings germinate, you've got a lot of predators that feed on those seedlings. Very high mortality risks. All right? So this is the survivorship curves. And if you were hearing me, with our survivorship curves, I kept talking about mortality rates because the two are basically linked. If you survive, then you didn't die. All right? If you died, then you didn't survive. So our survivorship curves have three types, and we can look at the mortality curves to kind of get a better idea as to when most of our deaths are going to happen. So our survivorship curves were all on the log scale. Our mortality rates will be QX, and we do them on the linear scale. All right, so mortality as a function of age. All right, so a type 1 curve has higher mortality rates early in life, not too high, and then low mortality rates throughout the bulk of their life until they reach old age. That's our mortality curve of a type 1 survivorship curve. You can see mortality rates are pretty low throughout the bulk of their life. This spot here is all due to just that heightened risk of the newborns. Type 2 survivorship. It's defined by constant mortality rates throughout life. It's a horizontal line for mortality rates. That generates this straight line survivorship curve. And then our type 3 curve looks something like this. Very high mortality rates of our young, of our offspring. But eventually, they get to the point where they have low mortality rates. Oftentimes, that's due to maturity. So by the time they're growing, and then all of a sudden they become adults, and at the adult stage, their mortality rates are low. And then I do have a slight uptick because we do have lifespans for these individuals. So as they approach their lifespan, that's going to go up. It doesn't go up as high because we've got fewer individuals. We've got fewer individuals. So these are the mortality curves. That are kind of like the let's see here. Can't find the word. I had the word I was going to say, but it's not quite right. We talked about survivorship curves. These are the opposite. These are the mortality curves. So survivorship and mortality kind of go hand in hand. Oh, almost. Let's get that up. Cut off that bottom. Whoops. All right. Questions? Make sure you know these curves. We'll talk about these survivorship curves again next week. Talk about some of these mortality curves. We're going to make life tables of humans. All right. We're going to do a static life table for a human population here in San Angelo. Well, no, actually, San Antonio, I believe. But we'll see what kind of survivorship curves we have for those populations. All right. Don't forget lab this week. We'll analyze our data. Have a good one.